is that really these coordinates q mu and p mu and so on do not commute. All right. So if you want, what happens, roughly speaking, is that once you try this induction, you sort of already perturb the space itself. So I mean, the best model that we know for it is non-commutative algebra. And the basic, very simple idea of non-commutative geometry, the following, is that our familiar duality between space, okay, space which is visual, and algebra is just a language which allows to think about this visual thing, okay? So this duality between space and algebra, which is that to space X corresponds the commutative algebra of coordinates on this space, in fact should be extended to allow for this algebra to be no longer commutative, okay? Now, of course, this is just, I mean, this example is just motivation, and what you need besides this thing is a principle which shows you that even in purely mathematical situations, not dealing with quantum mechanics, this extension of the duality between ordinary spaces and algebras is worthwhile. Now, this principle is extremely simple, and I want to state it in a sort of oversimple way, okay, so that you remember it. And so I will do it by taking a two-point space. All right, so my space will be just consisting of 2 points. Okay, and now I will ask I will take the ordinary commutative algebra point of view, and I will ask to identify these 2 points. You know, many spaces are in fact defined by quotients. I mean, subspace and quotients. These are the 2 basic operations. So let's look at the operation of quotient. We try to identify these 2 points. Now, the most naive way, of course, to identify these 2 points would be we consider the algebra of functions on these 2 points, and we take the subalgebra of functions which satisfy f of a equals f of b. Okay, this is the first way. This is the first naive way, taking functions which affect the same value at a and b. Now, it turns out that there is a slight variation on this thing, and it is the following. Instead of doing that, what you do is you consider the arrows that actually identify A and B, and you translate that algebraically. What does it mean algebraically? It means that instead of taking the subalgebra of functions taking the same value at A and B, what you do is you enhance the algebra. So these are the diagonal values, and you enhance it by adding to it off-diagonal entries. And then these things, this larger function algebra, you multiply it like you multiply matrices. Now, the effect of these 2 off-diagonal things is actually to do the identification, to perform the identification. These 2 algebras are equivalent in a mathematical sense, which is known as Morita equivalence, in this very simple example, which means that they have the same categories of modules. All right? However, as soon as you begin to look at examples which are a little bit more non-trivial than this 2-point case, you'll find that these 2 ways give different answers. And perhaps the simplest example, once again, I want to take really oversimple examples. So the simplest of such example is the following. I will just ask the following question. I take 2 intervals, 0, 1 intervals, and I want to identify them. Okay, I want to identify them, but I do not want to identify the endpoints. So these points should be different from this one, and that point should be different from that one. Now, of course, you cannot do that by the first method, because if you consider a function of any regularity, like smooth or continuous and so on, and if they have the same value inside, by continuity, they have the same value on the boundary. Okay? However, you can immediately do it this way, and what do you obtain? So what does this example give you? It gives you the algebra of, say, smooth maps from the interval 0, 1 to 2 by 2 matrices, of course, because we were doing the identification. But this function satisfies boundary condition, which is that such a function phi will satisfy that phi of 0 and phi of 1 are diagonal matrices. All right. Now, it's very easy to see that the corresponding algebras are not at all Morita equivalent. When you compute, for instance, the case theory of that algebra, you find something very non-trivial, while the other one is contractible. Now, you might think this example is far-fetched, but if you look at the principal series of the group SL2R, you'll find that the endpoint of the principal series is exactly a phenomenon like this. Okay? All right, so, I mean, of course, this example is, again, oversimple, and things really begin to make sense if you want them to be quite non-trivial by looking at more elaborate examples. And I have chosen deliberately to concentrate myself on one example. And this example is like a non-commutative elliptic curve, if you want. And it arises like this. It arises by taking a foliation of an ordinary torus. So you identify these two things. And you consider the foliation, which is given by the very simple rule, like dx equals theta dy. And so you can view it, if you want, a torus like this. And now what you want to do, you want to consider the space of leaves of this foliation. And you want to apply this recipe in order to obtain this space. Of course, every point on this transversal here gives you a corresponding leaf. So you might think at first that you will parameterize leaves just by a single variable, x. But of course, what happens is that that leaf comes back, so you have identifications. And if you compute what you obtain, you will obtain matrices, which are, if you want, indexed. So matrices F again, but which have two indices, like x and y. And x belongs to the circle, because this is a transversal, so x belongs to S1. And y, the only condition on y is that it belongs to the orbit of x, so it belongs to the set of x plus n alpha, if you want, where alpha is the rotation. Sorry, it's theta. Okay. So it turns out that when you compute this algebra of matrices, it has very simple generators. And so I can write now the first non-trivial example. And instead of writing it as a space, because you cannot see it as a space, I will write C-infinity functions on it. Okay? But I will give it a name, nevertheless. This is very important psychologically. Okay, so I will write C-infinity of this that will turn out to be non-commutative elliptic curve, which I will denote by T2 theta. It will have a modulus, which is this parameter theta. And this will be what? This will be an algebra of functions. Okay, it will not be commutative. But elements in this algebra will just be series, exactly like functions on an ordinary torus. Sigma of A and M, U to the N, V to the M, where the parameters here are complex numbers. And because of smoothness, they satisfy a decay condition, which is that A, as a sequence, belongs to the simple Schwarz space of functions of rapid decay on this square with two indices. Now, what I have to give you is, of course, the addition rule is obvious. Okay, when you add two things, you add the coefficients A and M. And I just have to give you the multiplication rule. Multiplication rule is non-trivial in the fact that when you multiply two of such expressions, you have to permute U and V through. And the rule for permuting U and V is obtained from geometry, from this construction. And it gives you the following rule, that VU is not equal to UV, but it's equal to exponential of I2 pi theta times UV. Okay? All right, and you see, so what happens is that you really have an algebra of functions. You can work with it. You can do computer computations and so on. You can do products and so on. And now you have to understand what happens. All right. Now, what really got the theory started, if you want, you know, the point of non-commutative geometry, of course, is not to extend classical concepts and so on to this situation. It's more complicated than that. The point is that there will be totally new phenomena in the non-commutative case, which have no commutative counterpart. This is really the important point. And if we look at the hierarchy of levels of understanding that we have of an ordinary space, okay? I mean, see? Okay, okay, put down, yes. Okay, so you see, there is, no, so let me write something very trivial on the reflection, okay? So something very trivial is the following, you know, when you look at a space, you can look at it from various points of view. The coarsest point of view is measure theory, okay? And then you have, say, topology, okay? And then you have, say, differential geometry. By this I mean the soft part of differential geometry. I mean, you know, Durham currents, and finally you have geometry per se, which is the metric, if you want, the metric aspect. Okay, so I mean, this is a very trivial sort of hierarchy of points of view, but it allows me to sort of structure a little bit what I want to say. And what I want to say is that even at the measure theory level, okay, there is a completely new phenomenon, which was really the starting point of the whole story. and which is the following very striking fact. So I will not talk about spaces because I will convey all the structure to the corresponding algebra, but there is an extremely striking fact which probably has not yet passed really the mathematical community, which is the following one, which is that in the measure theory, which means that it's only a certain kind of algebra which is considered, because you are not allowed to say what is a continuous function. You are only allowed to say what is a measurable function. Okay, so in the measure theory, an algebra, so it's a certain kind of algebra, they're called weakly closed and so on. An algebra A has a God-given time evolution. So it moves. Okay, I mean, it rotates. It's a very strange thing. There is an absolutely God-given homomorphism from the real line as a group to the group out of the algebra A, which is the quotient of the automorphisms of the algebra A by the inner automorphisms. Okay? And this group, roughly speaking, what one can say what it does, it exchanges left and right. So roughly speaking, I'm just, sort of an impressionistic equation, which is the following, which is that x, y will be equal to y times this group evaluated at the parameter extended to the complex domain to minus I of x. This is a basic equation. All right, and it turns out, I mean, I will come back to this much later, but in a sense, if you want, yes, sorry? No, of course, I mean, you see, the point is that it's exactly as in Riemannian geometry. To determine the group, you have to make a choice because it's only in the quotient. So you make a choice of what is called a state, okay, phi, and then you apply the state on both sides, and then the equation is true, okay? But because I wanted to, write an equation which is striking, I just wrote it without the state. Okay, sigma t phi is one parameter group of automorphisms. The main theorem is that it doesn't depend on the choice of the state modulo inner automorphisms. Okay? Minus I, it's in the complex domain. It's just this. Sorry? Yeah, no, but it extends by analytic continuation because it's a one parameter group of automorphisms. Okay? Okay, so that's if you want, that's the basic sort of striking feature, very striking feature of non-commutative geometry from the measure theory point of view. Okay? But of course, measure theory is extremely coarse. It forgets a lot of structure. So immediately what we want is we want to understand, for instance, topology and so on. Now what happens, if you want, is that when you look at this algebra here of smooth functions and so on, the first concept of topology, which admits an obvious generalization, but it's sort of obvious, to the non-commutative case, is the concept of vector bundle, or the corresponding classification, which is called case theory. And the reason why vector bundles admit such an easy generalization is that algebraically, a vector bundle on a smooth manifold is easily described by the space of sections of this bundle, because this space of section is obviously a module over the smooth functions. And the quality of this module has been sort of precise, if you want, by a theorem of Serens 1. They are exactly the modules which are finitely generated and which are projective. So they can, if you add a suitable module, they will become free. Okay? So if you want, this has an obvious counterpart. Now, why is it relevant? Okay, in the sense of Misha. Okay? Why is it relevant? It's relevant because the proof of the main theorem of case theory, which is Bott periodicity, becomes trivial when you extend it to this setup. You see? The first proof was given by infinite dimensional analysis and so on, some Morse theory and so on. But when you write it in the right context, which is the context of non-commutative algebras and so on, where matrices are available and so on, proof becomes very, very simple. So what we have these finite projective modules, and we have a very powerful Bott periodicity theory, which tells us that we have an exact hexagon, if you want, whenever you have an exact sequence of algebras. And now we have to give some existence to that by showing instances of such finite projective modules in our geometric example. Now it turns out that every transversal, that's every other transversal of the foliation, canonically gives you a finite projective module, so a vector bundle if you want, over the space, T2 theta. And I will just give you one instance, one example to make it concrete. Okay? So the example is the following. I will just pick my transversal to be the other one. So example. You see, what do I have to give you in order to give you an example of a vector bundle over the non-commutative torus? I have to give you the space of sections, and it has to be a module. All right? Now, what will be the space of sections? It will be a very familiar space, which is epsilon, which is the Schwarz space of the real line. We all know this space, okay? Space of functions which not only decay faster than any inverse polynomial, but all their derivatives do, okay? Now, this space, now we have to turn it into a module over this algebra. But this algebra is very simply presented, because it has two generators, U and V, and they satisfy this simple commutation relation. So in fact, I don't have to give you the action of any element. I just have to give you the action xi times U and xi times V, where xi is an element in Schwarz space. Now, xi times U, you compute it, and what do you find? You find that xi times U of S is just the exponential of 2 pi I S times xi of S.
Well, you compute the definition?
No, you compute it because the passing from the transversal to the module is canonical. So you compute it. No, you compute it. It's not definition. Well, here, anyway, you can take it as a definition, but what I mean is it comes directly from geometry. You don't have to invent it. Okay, and now you have the action of V, and xi V of S is simply xi of S minus theta. So if you want, the algebra is acting both by periodic functions and by translations. But the rate of translation is not commensurable with the periodicity condition, and that's why you get this commutation relation. Now, it's a non-trivial fact that you get a finite projective module. I mean, you know, it's not obvious that for this you need theta to be irrational. So it's not obvious that you get a finite projective module. And the next thing that you can do is you can ask simple questions about it. This is what I will do, okay? And the first question I will ask, you see, I will ask what is the dimension of this module, okay? So of course for that you need to find a notion of dimension of a vector bundle which is expressed algebraically. Now, the definition of dimension by number of generators is no good because it can happen that if you make the sum of the module several times, the number of generators drops. Okay? So in fact, the correct definition of dimension, you have to pass to a limit, and it is the limit, say when n goes to infinity, of the number of generators of the direct sum of the module many times divided by n. Okay? Okay, so now you take this example, you compute this, and what do you find? You find that the dimension of our module S, or epsilon if you want, is in fact the irrational number theta. Okay? So this is sort of first surprise. Okay? This is the first surprise. And you can have an equally equivalent surprise if you try to see the space from the point of view of Morse theory. Because if you try to see the space from the point of view of Morse theory, what will you do? You'll write a Morse function like Q plus U star plus some parameter times V plus V star. Okay, and then what will be the image of the space under the Morse function? It will be the spectrum of this operator in the algebra. What do you find? You find a counter set in most cases. So you see, when at first you have a very strange impression of irrationality of the space, because it seems that when you look at it, okay, you find these counter sets and so on, or you find this irrational number, and it looks really like a very difficult space. But in fact, it's not the case. And the thing that really got things started in 1980 was the following sort of integrality phenomenon, which emerged by doing computation. And this integrality phenomenon is the following. You see, because this example is so simple, it is not difficult to explain what is a connection and curvature for this vector bundle. And the point is that our space is a very simple space because a torus has parallel structure. So it has natural vector fields. And these vector fields, if I sort of intuitively think about this power series as being periodic functions on a two torus, okay, I can write the vector fields. They are given by two derivations. The first derivation is delta 1 of an element of the algebra, F. It will just be U d by du. I have to divide by 2I pi for reasons of normalization, and times F. So I suppose this is obvious what I mean. I mean that, okay, I differentiate like this, and delta 2 of F is equal to 1 over 2I pi v times d by dv of f. All right. Small remark, if I didn't insert the factors u and v, I wouldn't get derivations. Okay? Because algebra is not commutative, you have to be careful. Okay? These are derivations, they are natural vector fields on the space. And of course they commute that phi delta 1 delta 2 is equal to delta 2 delta 1. So the structure of our space is extremely simple. And what is a connection? Well, of course, the connection is given by two covariant differentials, del 1 and del 2. And del 1 should satisfy the rule that if we take a section and you multiply it by a function, you should have the Leibniz rule that it is del 1 psi of f plus psi delta 1 of f. And of course, a similar equation for del 2. Now, when you look at the example, okay, you find out that when you write down these equations, they have a very simple solution, which I will give you, because after all, del 1 and del 2 have to be operators on Schwarz space. So they cannot be very complicated. And the solution is just given by the following formula. You can take, as a solution, of course there will be many others, you can take del 1 of psi to be simply given by, exponential 2 pi I s, d by ds times psi of s. Okay, so the ordinary differentiation. And you will check this. This is very easy. And del 2 of psi to be given by, then you have to make a little computation. And it turns out to be 2 pi I s over theta times psi of s. All right. Now, this is one choice of connection. But, again, it's a very elementary exercise to show that there is a curvature, k, which is, del 1, del 2, minus del 2, del 1. And what happens to this curvature when you do a gauge transformation, namely when you change the connection, is quite simple to compute. And what you will find out is that the natural number, which is the integral of the curvature square, makes sense. What is the integral? You see, the integral is just like in Fourier, we evaluate the coefficients A00. It's a trace of the algebra. The invariant, I am going to Young Mills a little bit too early, okay? So just integral of k, okay? So you compute it in the example. Of course, this is topological, doesn't depend on the choice of the connection that you take. So you compute it in the example. Of course, you have to divide by 2I pi, as usual. And what do you find? Well, it's not difficult to see that the curvature of this connection is constant. It's a constant. This constant is easy to compute. It's just 2 pi I over theta. Okay? If the curvature is constant, the integral curvature will be the product of the dimension of the vector bundle by the constant. But the dimension is theta. Okay? And what do you get? You get theta multiplied by 2 pi I over theta. And of course, everything is divided by 2 pi I. So you get 1. Okay? And now this integrality, which was sort of at first found by integrals and so on, because there were explicit examples of projections, really got things started back in 1980. All right, what was sort of immediately done afterwards, if you want, which was needed, of course, was to understand all the corresponding notions and so on in the broad context of non-commutative geometry in general, of general spaces and so on. And of course, I mean, this gave rise to a dictionary, which is quite long, which allows you to read off classical notions to their counterpart in the general algebraic framework. And among them, if you want, there is a translation for the Chern-Weil theory. Okay? And the Chern-Weil theory translates into a theory which is cyclic cohomology. Okay? And I just want to mention one word about cyclic cohomology. Very simple word, which is that you can take it from two quite opposite angles, but you should have these two at your disposal. And these two quite opposite angles are the following, is that to understand cyclic cohomology, you should do one computation. There is only one computation you should do, okay, which is to prove a lemma. And this lemma has the same flavor as the Gauss-Bonnet theorem, as if you want, a number which is invariant under deformations. The dilemma is the following, is that if A is an algebra, of course not commutative in general, and the tau, I don't want to take a trace, it would be too trivial on the algebra A, so it will be a generalized trace, it will depend on three variables, tau of A0, A1, A2. is a 3 linear form on A. Okay, and I will ask it to satisfy two conditions, such that it satisfies two conditions. The first condition is cyclicity. So because the cyclic permutation is even in this case, it just means that tau of A1, A2, A0 is equal to tau of A0, A1, A2. Okay, if we were in the odd case, there would be a sign. And the second condition is asking tau to be a trace. But you know, to be a trace, you have more than one variable. So you have to write it as the following thing, tau of A0, A1, A2, A3, then minus tau. Now you put the contraction on the second term. Okay, and you keep going like that. Okay, and the final term is the only one which is tricky. It is plus tau of A3, A0, A1, A2. Plus or minus? No, it's minus. Okay, and now you require that this is 0. This is a trace condition. It's an obvious condition of cocycle flavor. And now what is the lemma? So what is the lemma that you have to prove? The lemma that you have to prove is that then the map which to E assigns the value of this monomial on E, tau of E, where E satisfies the equation E squared equals E. This is called an idempotent. So this map is homotopy invariant. In other words, if you deform this, okay, by keeping this equation, then the value will not change. Okay? And it's very simple to prove. You just use the fact that such deformation is isospectral, you write the corresponding condition, and then you get the result. Now, the abstract way to formulate this is that, in fact, we have a pairing between K-theory, okay, and cyclic cohomology, HC, of the algebra. And this gives you characteristic classes. Okay, so the final development which I want to very, very briefly mention in this sort of outlook on this example, if you want, is the following, is that, moreover, now you can write, I mean, you can ask yourself, can I find the good connections in general? Okay? And to find the good connections, the ones which are better than the others, it's clear that you have to write a variational principle. And this variational principle begins to hinge on the metric aspect, because it will necessarily now make use of the metric. And this variational principle now involves the integral of k squared. Okay? All right, so when you write the integral of k squared, indeed, now you are involving secretly the metric. Okay? And so this is functional. It shares all the properties of the usual Yang-Mills functional. And moreover, I mean, it has nothing special to this case. It applies in general. Sorry? Sure, I have to introduce it, you see, because when I write this, I am like using the combination delta 1 plus tau delta 2, where tau would be a complex parameter, which is the modulus of the curve. Okay? All right, so you do that, and you can, and then it turns out that there is a very new phenomenon, a very strange phenomenon, which has a lot of significance, which happens, which is that, you see, so let me write very small here. When you classify the finite projective modules, it turns out that they are classified. They are classified exactly as in the ordinary case by a pair of integers. So one is the first Chern class, if you want. And okay, the other has another meaning. And in fact, they form all the modules which are not virtual, which are true modules, not in K-theory, form the right half plane, so you have to exclude all this region. Okay, so it's all integral points which are located, and this region is specified by this line, if you want, is the line x plus theta y equals 0. Okay, so now you can ask, what is the Yang-Mills theory, and what are the Yang-Mills connections for any of these modules? And the theorem that we proved with Mark Riffel quite long ago is the following, is that the result is you take one of these points, and you write it as a multiple. You see, for instance, you could have taken this point. This point is twice this point. So it's the sum of two modules. Okay? So you can write it as a multiple of the module which cannot be written as a sum, okay, of two identical modules. So you do that, and you get an integer. Okay, you get some integer n if you want. Now the moduli space of Young-Mills connections, which minimize this, turns out by a theorem, if you want, that the moduli space, first of all, the moduli space is an ordinary manifold. Okay? And what is it? It is a quotient of the ordinary 2 torus to the power n divided by the symmetry group on an element. Okay. The moduli space of Young-Mills connection on the finite projective modules, which is labeled as I said here. Okay. I mean, this will have a lot of importance later. Background metric doesn't. Background metric will give you a metric on moduli space.
No, but you didn't introduce it.
Oh, the best way to introduce it is to give the analog of the d-bar operator. Okay? And the analog of d-bar is just the derivation delta 1 plus tau times delta 2, where tau is the usual complex parameter in the upper half plane. Now, let me just mention very, very briefly one thing, which is that these non-commutative elliptic curves, if you want, have 2 moduli. There is a moduli which is tau, of course, which is divided by PSL to Z. But there is another modulus which is theta. And it turns out that this theta also occurs modulo PSL to Z. And that the action of PSL to Z is exactly Morita equivalence. Okay? Now, all of this example was around for a long time and so on. And it's sort of, I mean, it became sort of quite important more recently. And it became very important for the following reason, which is sort of an accident, but a nice type of accident, which is the following, which is that people in M theory, string theory, are studying compactifications. And it turned out that when you look at M theory, in the 2 possible ways that we are able to look at it, one of them is matrix theory, and the other is 11-dimensional supergravity. Okay? When you look at it in either ways, it turns out that when you write down compactifications, okay, what you find is that the equation for such compactifications, I really don't have time to go into it, but it's exactly the equation for the Young-Mills connection on a non-commutative torus, on the nose. Okay, so this is what we found in the paper with Albert Schwartz and Michael Douglas. So on the nose, out of nowhere, you find out that there is a non-commutative torus occurring, and that the equation, moreover, for what plays the role of coordinates in this M theory is exactly the equation for the components of the connection, del 1, del 2, and so on. Okay, I mean, it's not extremely difficult to guess, if you want, because the equations have the following form, that you have coordinates in this theory, you have 9 coordinates, and you try to compactify them. So what you want is that x1 is equivalent to x1 plus a constant a1, and what you want is that x2 is equivalent to a constant added to x2. So what you want is a gauge transformation to achieve this. Now the first gauge transformation, let's call it u, it will be realized by an equation of this form, x1 plus a. And u will have to commute with x2, so u x2 is equal to x2u. Okay, and the second equation will be v x2 v inverse is equal to x2 plus a2. And v will have to commute with x1, so it will be vx1 is equal to x1v. Now, if you look a little bit at what happens here, you'll find that the multiplicative commutator, which is u, v, u inverse, v inverse, commutes with everything inside, so it has to be a scalar in the irreducible situation. And so you have this additional thing, and you can call this exponential 2 pi I theta. It's, of course, a complex number of modulus 1. And then you are back exactly to the previous equations. Okay? So this was, you know, sort of a... But then it turned out that for the development of the theory, there were 2, and then I'll go to my 4 problems, but there were 2 quite recent and important developments. The first development was by Albert Schwartz in a really remarkable paper with Nekrasov. Okay, and let me just say in one word what they found. What they found, you see, is that if you look at instantons in R4, classical, completely ordinary stuff. Okay, so you look at instantons in R4, and we know that because of concentration phenomena of instantons, that you will have, when you look at the space of instantons, you will have singularities where instantons can go to a point. So you can work out compactifications, you then back work out compactification and so on, but it's still singular, it has orbifold points and so on. Now there was a way from string theory to avoid that, and this way was developed by Seiberg and other people, and it was to consider the concrete ADHM a construction of the solutions of the Yang-Mills equation in 4 space, flat 4 space, and to replace in this equation something to be equal to 0, replace it by something equal to a non-trivial constant. Okay? But if you want, it was sort of ad hoc and so on. It was motivated by string theory and so on. Now, what Nekrasov and Schwartz have found, which is absolutely beautiful, is that this condition, modified condition that is equal to some constant, is exactly what you get when you work out Yang-Mills theory in a non-commutative sense on non-commutative R4. Okay? So, R4. Okay, so you take R4. To make it non-commutative, you need exactly what you have in string theory, which is this anti-symmetric that Yuval was talking about, field B mu nu. Okay, you put it down, and then you work out the Yang-Mills theory, and you find that you get exactly this modified condition. Okay, and the second thing is a preprint of Zyberg and Witten, which just came out 2 days ago, and which is non-commutative geometry and string theory, in which they sort of validate, if you want, the fact that this, which was at first a coincidence in the paper with Albert Schwartz and Michael Douglas, is in fact a completely general phenomenon. And that in fact what string theory, what the B field in string theory is doing is turning space-time to be non-commutative. Okay, this is basically what they have found. All right, so in the time remaining now, I want to go to these transparencies just to formulate problems which, of course, are very biased. Ooh. I think this came out, no? I think this no? Yeah, good. Right, so it's probably better to put down the light. All right, so I want to talk very briefly about 4 problems, which I consider to be, of course, I don't just want to give the problem, I want to give motivation why I think the problem is important. And the first problem, you can criticize it as being internal to the theory, but I will explain why it's not so internal to the theory. It is the following. You see that through the non-commutative space, of course, we have all these examples arising from discrete groups through the algebra of the group Lie groups, so their convolution algebra, group actions and foliations, and transiting through K-theory and C-star algebra. You actually get an invariant which is an abelian group. So you get a functor from all of these geometric objects to abelian groups. Then there is an obvious question, which is that, in fact, you know, it's very difficult to get such functors and so on, so it should be a classical thing. And in fact, we should be able to get it from standard geometry. All right? Now, as I said, there was this construction which, out of a closed transversal to a foliation, gives you a K-theory class. Now, this construction turns out to be extendable to a wider context. And for instance, in the case of discrete groups, it gives you a map which is called the assembly map, which goes from the K homology, not the K-theory, of the classifying space B gamma to the K-theory of the corresponding C-star algebra. Now, the problem, this map, as I said, is defined in the full context, including Lie groups, group actions, and so on. And the problem, which is called the BC conjecture, is to prove that mu is an isomorphism. Now, why is this problem interesting? It's interesting because it has 2 aspects. One aspect is injectivity, one aspect is surjectivity. Now, the injectivity aspect is a strong form of the Novikov conjecture on homotopy invariance and Weyer signature. It implies the Gromov-Laus and Rosenberg conjecture in the stable case. In the stable case.
I never actually was hiding everything.
Okay, fine, okay. Fine. All right. Okay, I will come back to that, okay? Now, the surjectivity of this map actually implies a number of things. It implies the Zellberg principle. When you apply to Lie groups, the Zellberg principle, you know, of vanishing of orbital integrals on discrete series, it implies the geometric construction of discrete series, a completeness, which is a difficult part in the Harish-Chandra theory. And it implies things like the Bass conjecture and so on. Now, there is recent work of Vincent Laforgue, the brother of Laurent Laforgue, and which has finally been able to cross an absolute barrier, which was before, which was that there was no example where the conjecture was actually proved, where the discrete group, let us say, was satisfying property T of Kazhdan. So I mean, this barrier was extremely difficult. And now it's proven. So it's proven for lattices in SL3, and it's proven for lattices in SL of periodic groups, for instance. But of course, Laforgue's proof gives a general proof for Lie groups semi-simple or periodic. And so, I mean, it gives a very conceptual understanding of all these results. Now, to answer Misha's question, I don't believe either that the general conjecture is true. And why should I not believe it? Because if it were true, it would tell you that all these invariants, in fact, are classical. They come from classical geometry. I believe that there is a lot more in, if you want understanding this star algebra, its case theory and so on, and that when we really understand it, we'll find it's different. Okay? But I mean, this is a gut feeling. Okay? And of course, we can discuss it. Okay? But of course, it's true for many, many groups. I mean, it's true for, there are plenty of groups. Injectivity, for instance, is proved for all lattices and so on. All right, the second question which I want to discuss, but this is even more speculative if you want, is the following. There is in non-commutative geometry an attempt to get the analog of Riemann's notion of a space, geometric space. There is such an attempt. And this is obtained as follows. You see, I want to make it very short. So in a sense, in Riemann's space notion, it's a conjunction of two things. You have a manifold, and you have the line element. Now, it turns out that understanding a manifold in topology, we understand it best from k-homology. Namely, it's a Poincare duality space, but not in ordinary homology. That's not enough, but in k-homology. So the data of the manifold is really the k-homology fundamental class, and the data of the metric is the line element. Now, it turns out very beautifully that these two things fit in non-commutative geometry. They are the same. And the k-homology fundamental class is given by the homotopy class of a self-adjoint operator. That's the definition of k-homology. Whereas this choice, specific choice of such a self-adjoint operator gives you the metric. The equation being that the line element is the inverse of D. Okay, so I mean, this gave rise to the notion of spectral triple. It's an attempt. I'm sure it's not the final notion of Riemann metric, but it allows you to think. Okay, it's a more general framework and so on. And in particular, when you look at the dictionary, you see, you find that when you look at diffeomorphisms of a non-commutative space, they have a finer structure than diffeomorphisms of an ordinary space. Why? Because if we think very naively as diffeomorphisms as being automorphisms of the algebra of coordinates, okay, that's what it should be. It turns out that because the algebra is not commutative, this group of automorphisms actually contains a normal subgroup, always non-trivial, which is a group of inner automorphisms. Okay, so it always has this structure. You cannot avoid it. Okay? Now, it turns out that when you look at the Lagrangian of physics that Yuval was explaining, well, this Lagrangian is the sum of two terms. One is the Lagrangian of Einstein's theory, okay? And the other is the Lagrangian of the standard model. Now, if you look at the group of invariants of this Lagrangian, what will you find out? You will find out that it has also two pieces. Because there is a gauge group of second kind, which is a group of maps from the manifold to the U1 cross SU2 cross SU3. That's one piece. But there is another piece, which is a group of diffeomorphisms. And it's not the product of the two groups, because diffeomorphisms shuffle the gauge transformations. It is a semi-direct product, so you also have an exact sequence, okay? And this exact sequence is like this. You see, it's one goes to maps from X to the small gauge group, goes to G, goes to diff. Now, of course, it's, you know, I mean, nobody can resist the temptation to say that these two exact sequences should be the same, okay? And amazingly, the names are the same. Because in physics, the gauge transformations are called internal symmetries. Whereas in mathematics, inner automorphisms, you know, it's into them. I mean, it's internal transformations. Now, it turns out that this, very naively applied, forces you, and this Yuval mentioned, to change your vision of space-time and to replace space-time not by an ordinary manifold, but by a slightly non-commutative enhancement, which is a tensor product of the algebra of coordinates that we know by a small non-commutative algebra, okay, which is very specific, but which is taken from experiment. It's taken from this Lagrangian, which is given to you and so on. But then when you work out, you find out that the gauge bosons that Yuval was mentioning, namely the photons, the W plus minus, the Z, the 8 gluons, and the Higgs, are just the internal part of the metric. Namely that when you compute what is the metric on this space, you find that it has, of course, internal part exactly as the group of inner automorphism was there. When you compute this internal part, you find exactly the usual bosons. All right, so the problem I would like to formulate this way, of course, this is naive. I mean, this is what Okay, it's, I take from physics, if you want. I take the Lagrangian and so on. But string theory is suffering from a very big defect that Yuval didn't mention, which is it doesn't make contact with the standard model, okay, so far. I mean, it predicts something which is enormous, there is no symmetry breaking, and so on. So the problem I would like to formulate it like this. Connect this phenomenological description. I mean, it has all the defects of a phenomenology with the appearance of non-commutative target space in string and in M theory, which I just mentioned and which is now really completely validated. And one thing I want to mention before I leave this transparency is that, you see, this connection with physics was extremely useful in understanding a number of subtleties about the notion of manifold in non-commutative geometry. For instance, there is no diagonal when you take a non-commutative algebra. There is a bimodule, and all of these things actually are almost forced upon you by the structure of the standard model. Okay, so let me now go to the two last transparencies. The first one is almost a joke, but so I will go extremely fast about it. So the first one is the following. See, it's almost a joke, but I ask you to think about it. Well, we know the local class field theory. It's a very nice theory when you consider non-Archimedean places. So what we are dealing with is the following. We are dealing with a local field, K is a locally compact field. Of course, a locally compact field has what is called a module. This module is obtained by looking at the scaling operation on the additive group. Okay? Scaling operation has Radon-Nikodym derivative, which is constant. This constant can affect certain values. These values form a group, which is a multiplicative subgroup of the positive numbers. And saying that the local field is non-Archimedean is exactly saying that this group is discrete. Turns out then to be generated by a prime power, which is Q. Now, the beauty of local class field theory in the non-Archimedean case is that there is an interpretation of the multiplicative group of K as a Galois group. And this Galois group arises like this, that you have, you take an algebraic closure of K, you take the maximal separable closure there, then you take the abelian closure, okay, and then you take inside the abelian closure, you take the unramified part, okay. Now, when you look at the Galois group of the abelian closure, it turns out that, of course, it will map to the Galois group of the unramified extension, and this group is topologically generated by the Frobenius. So if you look what Weil did, if you want at the inverse image of powers of the Frobenius, you get a group W, and if you want the result of local class field theory, which is best shown, I would say, by Brouwer's theory, is that this group is isomorphic to the multiplicative group of K. Now, when you go to the global field situation, I mean, needless to say, of course, this result doesn't hold when you take complex numbers, because complex numbers are algebraically closed. Okay? Now, if you take a global field, like the field of a function field over a curve, and when you take this global field to be of positive characteristic, exactly the same thing goes. Of course, it's much more subtle because it's global. But what you have the same type of extensions, the unramified extension, the abelian extension, and separable closure. And there is a subgroup of the Galois group of the abelian extension. And the main result of global class field theory now is that this group is canonically isomorphic to the group of ideal classes. Okay? Now, there is a paper of André Weil in a Japanese journal, I forgot, the Tokuma's journal, I think, in the end of the 40s, in which Weil explicitly mentions the defect, big defect, of our Galois theory so far, which is that there is no Galois theory interpretation when the characteristic of K is 0 for the connected component of identity in the Galois group of the ideal class group. There is no such interpretation. And if you think a little bit, you'll find out that there cannot be, because the Galois group is necessarily totally disconnected. If you think a little more, you'll know that it's totally disconnected because it's a projective limit of finite groups. It's a projective limit of finite groups because in the Brouwer theory, we only think about finite dimensional central simple algebras. Now, the beauty is the following, which I want to mention, is that the result on classification of factors, which came from this time evolution, can be stated like this, that in fact the classification of factors, I claim, is a correct Galois theory over complex numbers for the unramified part. It turns out that factors are simple central algebras over C. They cannot be finite dimensional. You have to take them approximately finite dimensional. Otherwise, you would get totally disconnected groups. And it turns out that they are exactly classified by their module, very similar to the module of a local field. And this module is a subgroup of R plus star. Okay? So what I propose as a challenge, as a provocation, okay, is go much further and do the missing part in this problem by veil. Okay? And I think that for the unramified part, factors will be essential. Okay, so to finish, I want to finish with Ras transparency.
You want to put the kind of filtering to find the prime filtering.
Exactly, exactly. So to finish, let me go now to the, no, sorry, not Riemann space. Okay, let me finish with this, which is again a provocative example. So let's start with a global field now. So we are dealing with a global field, and there is a very natural, though I mean it takes some time to realize that it is natural, non-commutative space, which is a quotient of adels. You know, a global field is defined by the existence of adels, which is in which they are co-compact and discrete. And you take the space of adels and you divide it by GL1K. Now this is a weird space, it's a very difficult space, so it's non-commutative space. And it turns out that there is a natural filtration of L2 of X, there is an L2 of this space, by infrared and ultraviolet cutoff, and that when you write down the validity of the trace formula, namely the fact that the limit of the cutoff trace on this space gives you the sum over all places of the local contributions which are predicted very easily from the Lefschetz formula, then it turns out that this formula holds for the global field if and only if the Riemann hypothesis holds not only for the zeta function but for all L functions simultaneously with Grossen character. Okay? Now there is, I proved a very easy case of this formula when you take finitely many places. In fact, I gave 3 different proofs of this. But recent progress, which I don't want to mention, is the following: is that in fact there is a beautiful interpretation, okay, of this. You see, the space X, you can think it's very weird. But the action of the ideal class group on the function space, in fact, can be interpreted simply in the sense of Ecke correspondence. I mean, they are not the correspondences of Ecke, but they are correspondence in the sense of Ecke, that 2 points correspond to several points, on the field K itself. For instance, if you take a function field, to the Frobenius or to every ideal class, you will associate correspondence, and the degree of the correspondence will be the module of the ideal, so it will be power of Q. It will have very similar properties to what we have usually, but instead of being correspondence on the points of the curve, it's correspondence on the field itself. So it's like quantum field theory, if you want. Okay? You are passing from the points to the algebra of all functions. Okay? And the problem, of which, of course, I mean, we all know about this problem, but what I want to say is that the problem, of course, this formula is true, for instance, in the function field case. But the challenge is to give a direct proof of this formula. And what I found is that I was totally on the wrong track when I was giving talks before. Because what I was doing was like trying to prove this formula. I don't have, yes. I was like trying to prove this formula. You see, this formula, I claim, will be much easier to prove if you take all L functions. I mean, you said that to me, but I didn't understand. Okay? Families, you know, and so on. So what I claim is that this formula will be much easier to prove if you take all L functions together than if you try to localize on a sector. Because if you try to localize on a sector, it's a little bit like if you were to understand the structure of a lattice by taking polar coordinates, you see? Which is stupid. It's totally stupid. Okay? So I mean, the challenge here is not to deal with the Riemann case, which is too difficult, but to begin by the function field case. We know it's true. And there has to be a direct proof, and I am fighting a lot with it. See? But this proof will be additive. And my mistake was to try to find a multiplicative proof. It was a big mistake. Okay, so I think I will stop.